video in Unit 3 for the Integrated Math 1 video series. In this video, we're going to talk about graphing linear functions, but before we do that, let's go ahead and try these 4 problems related to the problem at the top there. Okay, so in this particular situation, Tyra rents a moving truck for $38, plus $40 for each $40 for each day she uses it. Write a function that models her final cost for renting the truck for X days. And so, as we've talked about before with writing linear functions, we always want to start with that constant amount that doesn't change no matter how many days we use it, right? That $38 stays constant. It's our starting amount, right? If we rent the truck for 0 days, no time at all, we would still pay $38. So, so $38 plus 40 times x. And we're going to go ahead and call that f of x. As we talked about in our last video using function notation, we can think about that being f of x. Equals 40, because for each additional day, so for every increase of 1 in x, we pay another $40. And so that's why it's 40 times x. So we're increasing by multiples of 40 there, as x increases by 1 day each time. All right, is the cost increasing or decreasing with each increase in the number of days? So as the days increase, is my cost going up or is it going down? And of course, yes, it is going up. It is increasing. By how much is the cost changing each day? Well, it's increasing by $40 each day. Notice it's a positive 40 because we're increasing. And if it was decreasing by 40, we'd most likely put a negative 40 there because we're going down 40 each day. How much would it cost to rent the truck for 0 days? As I said a little bit ago, it'd be $38. That's like our initial starting point, and then we add 40 for every day thereafter. So we have a function, but let's see if we can graph this function, because that's our goal for today, is to graph linear functions and connect the graphs to real-world contexts. All right, so let's take a look. We have a graph here, and I've mainly plotted the first quadrant here. So this is the first quadrant, second quadrant, third, and then fourth down here. I should say most time, but a majority of the time we're going to be working in the first quadrant when we're dealing with real life situations. Others can occur, but the first quadrant is the main one. Okay, so along our x-axis, so go ahead and label things here. Along our x-axis, this is days down here, all right? Days that you're renting the truck. And then up here, along the y-axis, this is going to be total cost. Total cost. Now, I'm going to use different scales here. So for days, I'm just going to have it, each one. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so and then along the y-axis here, I'm going to go probably these, maybe use 20 as our scale here. 20, 40, 60, 80, 100, 120. And so on. Okay, so let's map this out here. So if we rent it for 0 days, then we're going to pay $38, right? So my graph's not going to be perfect here, but 0 days. So that's right here, right? On our y-axis here. So at 0 days, we're going to pay $38. So I'm going to put a point right here. And that is what we call our y-intercept. Our y-intercept is the point at which it crosses the y-axis. So our y-intercept here is the point 0, 38. Okay, that will always be that constant amount, that starting value, whatever you want to call it. Let me draw it right up here, f of x, I'll use that instead. 40x plus 38. This value here on the end, that constant value, will always be the y-intercept. Right? It's the y value when x is 0. The y value when x is 0. Okay, so let's continue on and plot some of these other points. So after 1 day of renting it, so 1 day, it's going to be not only 38, but 38 plus $40 for that 1 day that I've rented it so far. So 38 plus 40 is 78. So 78 is going to be like right in here. Okay? So that's the point 178. 178. Okay? After 2 days, that's going to be 38 plus 80, right? 80. 38 plus 80. So it's going to be 118. Right there. So on day 2, we're right there at 118. And then what's going to happen is it's going to continue to increase by 40 each day. So on day 3, we're going to add 40 to that. That's going to be 158. Right in there. Let's see. Sorry, 148. Okay, so right about there. Okay, so just making sure here. So should be 1. Let's see. Double check my numbers here. 38 plus 40 is 78. Plus 40 is 118. Plus 40 will be 58. So yeah, right in there. Yeah. Okay. So from there, we can think about like connecting these points here. So we've only plotted like the values of each day, but what if they charged us not by day, but by portions of days or fractions of days? So then we could think about what that would be. So if we graph this here, it might look something like that. Again, where our y-intercept is 38, and then for every time we go over 1 in the horizontal direction, we go up 40. Over 1, up 40. Over 1, up 40. All of these triangles are what we call congruent. They're actually the same triangle there. Same amount we go over, same amount we go up. But we could go over 2 and up 80, right? Would that be the same thing? Right? We could hop over to that one there. So this is where the 40 comes in. As I said before, every increase of 1 day increases 40 in the cost. So that's what we call the slope. So every increase in 1 in the day, so as I go over 1 to the right, that's increasing 1 day, I go up 40. So that's what we call the slope of a function. Okay? It's how much you rise every time you go over 1. Okay? So it's the slope or the steepness. It describes maybe if it's increasing or decreasing. The slope tells us a lot about the function. All right, so let's continue on. Let's look at this situation here. On July 30th, Jackie notices that the river behind her neighborhood is at a height of 24 feet. Then she notices that the water level decreases 4 feet per day. Write and graph a function to represent the water level of the river X days after July 30th. Okay, so what's our initial amount? Think about our function here, f of x. Our initial amount is 24. 24. but it's going down 4 feet. So for every increase of 1 in x, it should go down 4. So now we're looking at multiples of -4. So it's going to be -4x plus 24. All right? So let's go ahead and graph this. Again, -4x plus 24. So I'm going to do these with 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So this is 24 right there. Okay, and then these are our days here on the right. So 1 day, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so if we, again, go back to the same idea of our initial value, starting value, or your constant amount, whichever one you would call it, is going to be our y-intercept. So that 24, as we said a minute ago, this 24 is going to be our y-intercept. So we're going to start there. And then for every increase of 1 in x, we're going to go down 4. Right, that's our slope that we talked about a minute ago. So we're going to go down 4. So down 2 and then down 4 from there. So every time we go over 1, we're going to go down 4. Over 1, 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 down 4. And what we have here is we have this linear function right here. I'm going to go ahead and put my arrows because these are going to continue forever and ever in both directions. Now, I think the only part of this function that actually applies in our situation is from 0 to maybe 6. So 0 is when she first spots the river and the height of the river, and then it goes down, down. And then at day 6 is actually when the water level is 0, meaning it's completely dry. But we can't have like a negative, like a day 7 is down here negative. We can't have a negative height of water levels. So the only part that makes sense here is maybe from 0 to 5 days. But that's how we graph a linear function. We have the y-intercept, which is the constant amount, and then we have our slope, which is how much it's changing by with every increase of x. So I wanted to give you a way to kind of see this dynamically. So if you go to Desmos.com and you hit the graphing calculator feature there, it'll take you to something like this, and you can type in, I'm just going to do y here, y equals, let's start with -4x plus 24, I think is our function, right? If we zoom out here, we can see that same graph that we just got done doing, right? Y-intercept of 24, x-intercept of 6, the same exact graph. So you can use technology to help you do something like this as well. I'm going to change this though. I'm going to delete this and put y equals mx plus b. When I type in mx plus b, so I'm putting m for the slope and b for that constant or y-intercept. And it says, do I want to create a slider for m and b? It knows that x is our variable, but it doesn't recognize m and b. So it says, do you want to add a slider? I'm going to click yes for all. And what's going to happen is it set both of them at 1. I'm going to change b to 0, just to make it 0 there. And what we can do is we can change both of these and kind of see how it impacts the graph. So as I increase the slope, so I'm going to leave b alone for right now. I'm going to increase m. As I increase m, look what happens. It gets steeper and steeper and steeper and steeper and steeper. As I decrease m, it gets less steep. And in fact, what happens when I make this m, this slope negative? There's 0, and then negative. Oh, okay, now I'm decreasing. When the slope is negative, I'm decreasing as I go from left to right here. So you can see that happening there. Okay, so now I'm going to leave the slope alone, and now I'm going to just change the y-intercept. So it is the b value. So as I increase that, that's all that's happening, is the y-intercept is changing as I change b. So you can kind of make any linear function you want just by changing, these two parameters in this Desmos activity. Okay. Now, also I'm going to put this link in the description or in the PlayPosit video to this marble slide activity for linear functions. So in this type of activity, you want these balls, when they're released, to go through the stars. If I hit launch right now, they're not going to go through the stars because it follows the linear function all the way down. So what we're going to do is we're going to edit the linear function over here on the left, and I'll bring this forward so you can kind of see what I'm editing here. We need to change this linear function so that it is down here. You might picture it coming down and then hitting the linear function here and going over. So what we want to do is we want to just shift this linear function down. Okay? Do we need to change the slope? No, right? We just need to shift it down. So we don't need to change the 1/2 here. We just need to change the 1. So let's see if we can come up with a value. Let's see, if we were to move it down and it follows here, what would the y-intercept be? Maybe -2? If you can kind of picture that, -2, let's try it. So let's delete the 1 and let's change it to -2. Ah, there we go. Okay, so let's see if that works. Let's hit the launch. And there we go, right? It works. So you can kind of play with those two parameters, the slope and y-intercept, and see if you can make things work for these marble slide activities. Let's do one more, and then we'll finish up. Okay, so on this one, kind of same setup a little bit here, but this time, if I move this line up or down, it's not really going to work, right? This time I actually need to change the slope. I need to change the steepness of the graph so that the ball goes along that line and follows the stars here. So let's see. What would a good slope be? Let's see. For every increase of 1 in x, how much do I need to go up? Well, for every increase of 1, so I'm just going to go over 1, how much do I need to go up to be kind of along that line? So over 1, up, maybe like 1/2 of a unit. Let's try that. So I'm going to delete the 4 and do 1 divided by 2. Okay, good. All right, I think that's going to work. We launch, and there we go. So this is actually the same slope as the one we just did a minute ago. So let's do one more where I have a little bit different situation here. Okay, so in this particular situation, we've actually added a parameter, or not a parameter, but a domain restriction to this. So if you use curly braces, that's on the right side of your keyboard. You can open curly brace, and then they type x is less than 4, and then close the curly brace. What that tells us is we've got our linear function here, but they've restricted the domain to only x values less than 4. So all x values less than 4, we see the function. All x values equal to or greater than 4, we don't see the function anymore. So we've limited the domain in this particular situation. So let's see what happens right now when we launch it. Okay, that's pretty good. We got 2 of the stars, but let's see if we can get all 4 here. So let's see. If we were to increase the domain restriction to go all the way to maybe like to this star here, so like 7.5, it might continue because we can't go further than that because that won't get that last star. So let's maybe increase it to maybe like 7.5. So we change the 4 here to 7.5, And that's gonna make sure and get that last star, and then we think that it might shoot off and get this last one. Let's see. All right, good. Okay, so we've got it, right? Hopefully you're getting the hang of this, and maybe you can try it yourself sometime, all right? So continue to work on that marble slide activity, but again, hopefully you've reached our goal for today, which was to graph linear functions and connect graphs to the real world context. So we start with real world context, we create the function for it, and then we can plot the graph based on the y-intercept and the slope that we have for that function. All right, so thanks for joining us in this video. Hopefully we'll see you in our next video in this Integrated Math 1 video series.